This is EE698I, Mixed Signal IC Design, and this is lecture number 8. In the last class, we were discussing about how to characterize the ADC, and we saw that we take the ADC and feed a sinusoidal signal at the input, right? So if you look at the spectrum at the output of the ADC, it will look something like this. So let's say this is the bin number K. We will have one impulse corresponding to the input sinusoidal frequency. And due to the circuit implementation, we'll also have non-linearity. So we'll have harmonics of this input signal, right? And the other bins will be filled by the noise. Okay. And this noise will be both due to the quantization noise and the random circuit noise. We saw two metrics to characterize the ADC. One was the signal to noise ratio, where we take the ratio of the signal power, that is the magnitude of this bin, to the noise power, which is the sum of these bins. Okay. So here we do not include the strength of these harmonics. The second metric is the signal to noise and distortion ratio, or SINAD. So here we take the ratio of the signal power, that is the strength of this bin, to the sum of both the noise and the distortion products. So we'll take the sum of all these bits, including the harmonics, right? And we saw that we also compute the effective number of bits based on this SNDR as SNDR minus 1.76 by 6. So many bits. Okay. So let's now see a couple of other metrics. So one is called the Spurious-free dynamic range. So this says how much is the highest spurious tone, that is any tone besides the desired input tone. Okay, so here this is the desired input tone. So any tone beside the required input tone is a spurious tone, and the spurious-free dynamic range says how much this highest spurious tone is lower than the input tone by, right? So let's say if this is plotted in dB scale. So this is my highest spurious tone, right? And this directly gives me my SFDR in dB. Okay. So in this particular example, the spurious tone is the harmonic of the input signal. But in practice, we can also have coupling from some other signal from in the system. So you can get spurious tones at some other frequency, say maybe somewhere here also, right? And this could be higher than the harmonic, right? So in that case, this is the spurious tone, right? And this will give the SFDR. Okay. So let's look at one more metric, which is called the dynamic range, abbreviated as DR. Okay. So this says what is the ratio of the maximum sinusoidal input amplitude you can apply to the ADC to the minimum input amplitude. And this is as usual represented in dB. So you take 20 log of this quantity and say dynamic range is so much dB. Okay. Well, we know that if the ADC can operate from minus Vref to plus Vref, that is say minus Vref to plus Vref, the maximum input amplitude is Vref, right? So the input sinusoid can span plus Vref to minus Vref. That is the maximum amplitude. So the maximum amplitude is usually the full scale voltage, which in our case is equal to Vref. So there are multiple ways in which you can define what is the minimum input amplitude, and the usual definition is that we say the input amplitude is the one at which we get an SNR of 0 dB. That is the amplitude where the signal power is equal to the noise power. Okay, so any amplitude below this minimum amplitude, what we'll have the signal power to be lower than the noise power. So we can't properly distinguish between the signal and the noise. That's the overall idea. Okay, so how this is computed is as follows. So we will plot the signal to noise ratio in dB in the y-axis, and we'll plot this with respect to the input amplitude. Okay, and the input amplitude is plotted in log scale, and it's plotted in something known as dB full scale, that is dBFS. Okay, so what is done here is that if, let us say, your input amplitude is A, you normalize this amplitude with respect to the full scale. That is, you take A and divide by the full scale voltage, which in this case is Vref. Okay, and you take 20 log of this and say the input amplitude is so many dB with respect to the full scale voltage. Okay, so 0 dBFS is the maximum input voltage you can apply, right? And if you take a voltage 0.5 Vref, that will be minus 6 dBFS and so on, right? So now if you plot this input amplitude versus SNR, you ideally expect a straight line, right? Because if you increase the input power by 1 dB, you also expect the signal to noise ratio to increase by same 1 dB, right? So this line will have a slope of 1 dB per dB. Okay, and in this plot you find where is the SNR of 0 dB, right? And you find that this is the minimum amplitude, and this range is the dynamic range in dB. Fine. Before moving to the next topic, let me quickly clarify something. So in the last discussion session, one of you asked a good question, which is the following. So the question was, hey, till this point we have been using sinusoidal signals for characterizing the ADC, right? But in practice, we'll not be always encountering sinusoidal signals, right? So what's the point of this, of using sinusoidal signals? And in real life, how would you characterize the ADC? Okay. So the answer to the question is, the standard way to characterize the ADC is by applying sinusoidal signals. And the reason we do this is because it turns out that generating clean sinusoidal signals is relatively more easier than generating any other kind of signals. Okay, and since we are trying to characterize the ADC alone, the signal that we feed into the ADC must be very clean. Okay, this itself should not contain a lot of noise, right? Only then we can distinguish, or only then we can properly find out how much noise the ADC itself is adding, right? And so if you apply such a pure and clean sinusoid, as we saw in the spectrum, we will have one impulse corresponding to the input sinusoid. We will have harmonics, and then we'll have the noise, right? So here it's quite clear as to what the signal component is, right? And what are the nonlinear products or the harmonics, and what is noise, right? So we can clearly distinguish each of them, and so we can easily characterize how much noise the ADC is adding and how much is the nonlinearity of the ADC. Okay, but let us say instead of the sinusoidal signal, you feed the ADC a modulated signal, right? Which is what something you will encounter in practice, something like this. Okay, So the signal spectrum will occupy the entire band, right? So you'll not be able to distinguish what is signal and what is noise. Okay. So in that case, you can ask, well, what if I don't apply the signal at all? In that case, I'll get only the noise, right? So by integrating this spectrum, I'll find what is the noise power. Then I can apply the signal, integrate the spectrum, find the signal power, and then I can find the signal to noise ratio. Well, you can do this, but when you apply the signal, you will not be able to distinguish how much the signal is getting distorted. That is, what is the non-linearity added by the ADC, right? So it is not trivial to characterize the non-linearity of the ADC by applying such a modulated signal. Okay, and that's why I use this pure sinusoidal signals for characterizing. Okay, and of course, you know that any signal can be decomposed as sum of multiple sinusoids. That is the Fourier decomposition. So if you know how the ADC responds to a sinusoidal signal, right? In principle, you can sit and work out the ADC's response to any other signal, right? And in practice, let us say you are using this ADC in a wireless receiver. So you will have something like this, right? Antenna, some amplifier, some mixer you have, some filtering you do, and then you give the ADC, and then you do some demodulation in digital, right? And in such a real system, the input to the ADC will not be a sinusoidal signal. It will be this kind of some modulated signal, right? But in this system, what we are interested is finally will be something else. That is, here we may be interested in bit error rate or symbol error rate, right? So what this means is that this is the receiver, right? So in the transmitter, we'll be transmitting some symbols or some bits, right? And after demodulation, we will find what is the percentage of error we are making, right? And that's what is of interest to us finally, that is BER. Okay, and it turns out that this sinusoidal SNR that we measure for the ADC will determine what is the BER we get in the overall system also. Okay, so for a given BER and for a given modulation scheme, it can actually be found what is the minimum signal to noise ratio you need for the ADC, right? And based on that, you design the ADC, right? That's how it happens in practice. Okay, so the bottom line is the standard way to characterize the ADC is by applying sinusoidal signals, right? Because that is how we can clearly distinguish how much is the non-linearity added by the ADC and how much is the noise added, right? And in the bigger system, this SNR that you have measured will determine some other bigger parameter in the system, right? For example, bit error rate in this wireless receiver. Okay, and this bigger parameter is what is of interest to us, and this will in turn depend on this signal to noise ratio that we measure like this. Okay. Till this point, we were dealing with signals. We were dealing with cases where we were testing the ADC with sinusoidal signals, right? So this is like a dynamic characterization of the ADC, right? Where the input is varying. Okay, but in many cases, we might also be interested in characterizing the ADC with DC inputs. Okay, because we might want to digitize some DC signals. Okay, so in that case, how do we characterize the nonlinearity of the ADC? Well, if we try to resort to the same method as we did before, what we'll do, we'll give a signal at DC and look at the spectrum, right? And DC corresponds to a frequency of 0, which means all the harmonics, that is the third harmonic, fifth harmonic, everything will also be at 0, right? So we can't distinguish anything. So how do we do? Well, if you take any system to characterize it for DC, what do? We apply the input voltage as DC and keep varying the amplitude, right? And measure the output for each input DC And if the system is linear, we'll have a linear characteristic like this. So this is my output voltage, right? And if it's not linear, we'll have some kind of nonlinear response, right? And this is how we can find and characterize the nonlinearity of the system. And that's exactly what we will do with our ADC also. Well, if you remember, this was the staircase characteristic of our quantizer, right? So here I'm considering a mid-rise quantizer, okay, with total of 8 levels. So the full scale range of the quantizer is from -1 volt to +1 volt. So in the x-axis, I'm showing the input voltage, right? And in the y-axis, I'm showing the output codes. Okay, and the codes range from 0, 1, 2 till 7, right? And we also saw that this width, that is each of this width, is equal in an ideal quantizer. And this was defined as delta, that is the step size of the quantizer. And in this example, what delta is? Well, we'll have to divide this range from -1 volt to +1 volt into a total of 8 equal steps. So the step size is 2 by 8, that is 0.25 volt. Okay. And please note that here, the step size for each of the codes is same and is equal to delta. Okay, so the step size same for all codes. Okay. So because of this, if you try to fit a curve for this characteristic, we can easily fit in a straight line, right? We didn't draw it properly. So a straight line like this, right? And that is why we are modeling the quantizer output as the input plus the quantization noise. So the other way to think about this is that if you look at the same characteristic from a large distance, that is, if you zoom out this curve, you will not be able to see these jumps, right? You will essentially see only a straight line. Okay. Or let us say you squeeze in more and more levels within this range of -1 volt to +1 volt, such as the case here, where I have 64 levels between the same range. We can see that it is looking more and more like a straight line, right? And if I have more levels, say here I have taken 1024 levels in the same range, this basically looks like a straight line, right? And only when you zoom into each portion, you can see this staircase jumps. Okay, and we are able to see this kind of a straight linear line because the step size for all the codes is same. Okay, and a bit of terminology. So this step size here is also called the LSB size, where LSB stands for the least significant bit. And this is called so because this delta is the change in the voltage you need to change the output code by 1 LSB, right? From say 0 to 1 or 1 to 2 and so on. The input voltage has to change by at least delta, right? And these points where we see abrupt changes in the quantizer characteristic, so these voltages are called the transition voltages. Okay. And let us say for the kth code, I call the transition voltage to be Vk. What is this? So each of these voltage, that is these, right? And each of these transition voltages is spaced by delta apart, right? So which means for the kth code, it's going to be k minus 4 times delta, right? Because I have 4 codes in the negative side and 4 codes on the positive side. Okay. So we can simply quickly verify this. We know delta is what? 0.25 volts. That's my delta. And if I look at the code 1, that is if I use k equal to 1 here, right, what I get? I'll get minus 0.75, right? And that's exactly the transition voltage for the code 1. right? This is 0.75 minus 0.75, right? So for k equal to 1, Vk is minus 0.75 volt. Similarly, for the code 4, right, the transition voltage is 0, and that's what we get. Okay. So ideally, this is the kind of characteristic we desire from a quantizer. That is, all the codes must have the same step size. But in practice, this is not going to happen. And what we will get is some kind of a characteristic like this. That is the curve I'm showing in red. Right? So what has happened here, the step size or the code width for each of these code is different, right? So in the ideal characteristic, that is the one in red, and that is the one in blue, you clearly see that the step size is same for all the codes, whereas for the one in red, the step size is different for each code. Okay. So now if you try to fit in a curve for this red curve, red characteristic, you will get some kind of a non-linear curve like this, right? So something like this. And this is what results in non-linearity or distortion. Okay. Again, the other way to look at it is that if the same characteristic is viewed from a large distance, you will only see a non-linear curve. Okay. So now, how do we represent or describe such a non-linear quantizer characteristic? Well, one way is to say what my transition voltages are, right? So ideally, these were my transition points, right? So these points, right? But now they have been shifted to these voltages, right? So one way to describe this quantizer characteristic is to say what the transition voltage for each code is, right? And the other way is to say what is the step size or the code width for each code. That is, we'll say, for code 1, this is the code width or the step size. For code 2, this is the width, and so on. Okay, and what is the code width or the step size for a particular code? It is the difference between two successive transition voltages, right? So for example, if you consider code 2, right, this is the code width or the step size, right? And what is that? It is the difference between the transition voltage for the third code, that is this voltage, minus this voltage, right? So the code width or the step size for the kth code is Vk plus 1 minus Vk, right? So this is one way. I mean, these are two ways in which you can describe or represent the quantizer characteristic. Okay, but what we are interested in is to represent how much this quantizer characteristic has deviated from the linear characteristic. Okay, so how can we do that? Well, we'll say how much the transition voltage has deviated from the ideal transition voltages, right? And for the ideal case, please recall that the transition voltage was this, right? K minus 4 times delta. So what we will do is we'll say the deviation for each transition voltage is so much. Okay. So similarly here, instead of showing only the step size or the code width, we will say how much this has changed from the ideal value of delta. Okay. So please note that both these quantities have dimensions of volts. Okay. So which means here I am considering an ADC that is operating from minus 1 volt to plus 1 volt, right? So now let us say if I make the same quantizer, and if the ADC is operating from say minus 5 volt to plus 5 volt, okay, so these values, that is these values will be higher, right? But this doesn't mean that the ADC running with this minus and plus 5 volt has a larger nonlinearity or a higher nonlinearity, right? And this is happening because we have not normalized this quantity, right? So to have a fair comparison, what we do is that we take these quantities and normalize this to the step size delta. Okay, and this quantity is called the integral nonlinearity, and often abbreviated as INL. And this guy is called the differential nonlinearity. or DNL. And both these quantities are usually represented in terms of LSBs. Okay, well, technically, both these quantities are dimensionless, right? But in practice, we will say that this INL and DNL is so many LSBs. Okay, so that's because you can think of the step size delta as so many voltage for a one LSB transition, right? So although the actual dimension is volt, you can sort of think of it as some volts per LSB, right? So this is volts and this is volts per LSB, and this is so many LSBs, right? So the final quantity will have, you can say that it has dimensions of LSB, okay? And please notice that this DNL here, that is this differential non-linearity, what it explains how much the step size for each code has changed, right? So it shows the variations in the quantizer characteristic in some sort of a local sense. It gives you an intuition, or it gives you some, like explanation regarding the local variations in the quantizer characteristic. Whereas this INL shows how much these transition voltages has varied, and it gives you some kind of a global picture. Okay. And since both DNL and INL represent the same quantizer characteristic, both have to be obviously related, and it is not difficult to find the relation. Okay, so INL of K is what? Vk minus K minus 4 delta by delta. That is for this case. And DNL of K is what? It is Vk plus 1 minus Vk minus delta by delta, right? So if I take INL of K plus 1 minus INL of K, what do I get? I get Vk plus 1 minus K plus 1 minus 4 times delta, right, by delta. So let me push it to the left, minus Vk minus K minus 4 times delta by delta, right? And this you can simplify it to be Vk minus 1 minus Vk minus delta by delta, right? And this is simply equal to DNL of K, right? So the other way to think is that INL is an accumulated version of the DNL, right? Because here we notice that DNL is the first difference of the INL, right? So which means the other way also holds good, that is INL is an accumulated version of the DNL. And that is why these are given these names. One is differential nonlinearity and other is integral nonlinearity. Okay. So now let's do a quick example. So here I have shown the same quantizer characteristic, and I have also shown what are the transition voltages. Okay. So let's try to compute what the DNL is. And please note that the ideal step size is 0.25 volt in this case. Okay. So let's do it for all the codes. And let's first find the code width or the step size for each code. Okay. Well, for code 0, what is the code width or the step size? Here we can see that for code 0, any voltage from minus 0.75 to minus infinity will be mapped as 0, right? Which means you really cannot define what is the code width for code 0. So generally we don't define the DNL for the first code, that is code 0, as well as for the last code, right? So I'll just put not applicable or it's not defined. Okay. So what about code 1? Well, so this value is 0.65 roughly, and this is 0.4 minus 0.4. This is minus 0.65 and minus 0.4. So the code width is 0.25. What about second code? So this is minus 0.4. This is minus 0.3. So this is 0.1, right? And what about code 3? So this value is minus 0.3, this is minus 0.1. So this is going to be 0.2. Again for code 4, this is minus 0.1, this is 0.3. So the width is 0.4. So for code 5, we have 0.3 and 0.4. So that's again 0.1. And for the sixth code, it's 0.4 to 0.75. So the difference is 0.35, right? So how do you find the DNL for each code? Again, for the 0th and the 7th codes, it is not applicable. So for the first code, we'll take this 0.25, that is the code width, subtract it from delta and divide by delta, right? And what is it? This is going to be 0, right? So similarly, you can do for the other numbers. So this is 0.1, so this is going to be some negative number. This is also going to be negative. This is positive, negative, and positive, right? So you can plot the DNL. This is the code, right? From 1 to 6. So now let us take a look at this quantizer characteristic and try to find the DNL for code 3. So how do you do it? Well, first we need to find the code width or the step size for that particular code, that is the third code. So let's look at the third code, that is this. Well, we surprisingly see that this code is not even occurring in the characteristic. In other words, this code is entirely missing, right? So what is the code width for this? Well, there is 0 voltage range, right? That is the total range of voltages which is getting mapped to this code, that is code 3, is 0, right? So essentially the code width is 0. So DNL of 3 is the code width, that is 0 minus delta by delta, which is minus 1. Okay, so which means if at any code we get a DNL of minus 1, it implies that the particular code is missing, right? So we'll say it is a missing code. And obviously this is not something we want. So we always try to ensure that DNL is less than minus 1 LSB. Okay. In practice, besides these errors of having non-uniform code width for each code, we also have a couple of other errors. So one is called the offset error, where the ideal quantizer characteristic, that is the one in blue, is shifted to the left or right by a constant amount. Okay, so note that here again, the step size for each code is still same and equal to the ideal value of delta, right? What has changed is that all the transition voltages here, right, they have all been shifted by a constant amount, right? So a small amount of offset error is usually tolerable in many practical systems, and it can also be corrected easily, right? And since this offset affects all the codes in a similar fashion, it does not introduce any non-linearity, right? Because you still see that it is a straight line. Okay. The other kind of error we can get is the following, where the step size for all the codes, that is these, they are all equal. That is, say delta 1, delta 2, everything. That is the step size for all the codes is equal and equal to some value delta hat. But this delta hat is not equal to the ideal step size delta. Okay, so here you can see that the step size, ideal step size is this, right? So this much. But in the red characteristic, the step size is only so much. It is smaller than the ideal value of delta. But the step size for all the codes is equal to this same value. Okay. So if you try to fit in a straight line for the blue curve, you might get a line like this, right? Whereas for the red curve, you might get a straight line like this. Okay. So what has effectively changed is the slope of the characteristic, right? So this only results in a gain error. Okay. Again, a small amount of gain error is usually tolerable in many practical systems, simply because this again has not introduced any non-linearity, right? Because this gain error is affecting all the codes in a similar fashion, right? But in reality, we will have a combination of these. So for example, here we have a combination of a gain error and non-uniform code bits. Okay. So in this case, before computing the DNL and INL, we will have to correct for this gain error. Okay. Because let us say if you don't account for this gain error, so and you try to compute the DNL, what you will do in this case, you will say DNL of any code K is equal to the step size or the code bit for that particular code, which is equal to this delta hat minus the ideal step size delta by delta, and you will say that this has some DNL, right? But of course, we clearly saw that this has not introduced any additional non-linearity, right? It has only changed the linear slope. So what do we have to do? Well, instead of using this ideal step size delta here for calculating DNL, we need to use the step size delta hat here. So this will give you 0 DNL, and that's what you sort of expect. Okay. So we need to do a similar thing here, but this curve is not so trivial as this curve that we can find this delta hat, right? So instead of finding this delta hat, what we can do is find some kind of an average step size. Okay. So how can that be found? Well, note that the characteristic in gray, that is the ideal quantizer characteristic, right? And let us say this is the ideal transition point, right? The first transition point for the ideal characteristic. And this value is what? This is minus 0.75. And this is the last transition voltage for the ideal curve, that is plus 0.75. Okay. And in between these, we have a total of 1, 2, 3, 4, 5, and 6 codes. So the slope for the ideal characteristic is around 6 codes by 1.5, right? Now for the non-ideal characteristic, that is the one in red. So the starting transition point is still same, that is 0.75, minus 0.75. And the last transition voltage, say that is around, say 0.45. Okay. Again, in between these two, we have 1, 2, 3, 4, 5, and 6 codes. So for the curve in red, the slope is again 6 codes by difference between 0.45 and minus 0.75, and that's around 1.2. Okay. So which means that the step size delta average, it is smaller than the nominal step size delta, right? And how much this is smaller by? This is smaller by this factor. Okay. So we need to use this delta average here for finding the DNL and INL. So then you can find the DNL as Vk plus 1 minus Vk minus this delta average by delta average. Okay, so many LSBs. That's how you find the DNL. Okay. And of course, in real life, you will have a combination of all, right? So in this curve, we have offset error, gain error, as well as non-uniform code bits. So we have all of them. So in this case, to find DNL and INL, first we need to correct for both offset and the gain errors. Okay, because let us say you don't correct for the offset error, what will happen is the following. So here we have considered an ideal quantizer curve that is just offset by some voltage, right? So here if you try to find the INL as it is, what you will do is that, well, I will say for this code, right? For this code, the ideal transition voltage is this, but the actual transition voltage is this, right? So I will say this as my INL, and that's not completely correct, right? So what we have to do is that we need to correct for both the offset and the gain errors before you compute the DNL and INL in practice. And the usual way or the standard way to do this is as follows. So for this curve, that is the one in red, you try to fit in a curve of the form V is equal to U naught plus alpha 1 times U. So this U naught here gives the offset, right? And this alpha 1 gives the slope. So what you do, you correct for this offset error, that is you subtract V naught from the quantizer characteristic we got, okay? And then use the slope to find what is my delta average. And using this delta average, you then compute what is my DNL and INL. This is how you do it in practice. Okay. So let's stop here and continue from the next class.